quiero hablar en inglés, es más fácil. También puedo explicar más mejor, pero la presentación es en español. ¿Tienen algunas preguntas, por favor?
Yo ayudo con las preguntas.
Okay, hoy hablamos sobre cerrar la brecha entre la planificación de la vida de la mina y implementación de operaciones, particularmente en referencia a life of mine planning, la vida de la mina. La vida de la complejo es muy importante. Okay. So, I'm referring to life of mine planning, and what exactly are we trying to accomplish through life of mine planning? What we're trying to actually do is determine what the ultimate reserve is. And specifically, we do that by determining the stages of design that we'll be applying to the mine. In terms of development, sequencing of major reserve units. Today I'll talk in terms of in terms of open pits. So we'll be talking about benches within the limits of each one of the stages. And then an annual production schedule that will in some way maximize the value to the stakeholders, to the owners. Now, the way this is actually implemented in practice depends upon the end user, depends upon the application. So, in terms of new projects, greenfield studies, the objective is usually to evaluate the project value, with a decision coming out of the evaluation to either sell the project or to move on to the next stage of expenditure and development. If we're talking about existing operations, we have a completely different perspective. Here, for a brownfield project, what we're trying to do is we're trying to determine a life of mine plan that will also maximize project value. But in this case, it needs to be a plan which we have to implement at successive levels of increasing detail so that we can eventually go from the life of mine long-term plan to something which is operationally feasible. In other words, we have to reduce the level of detail that we've created on annual schedules and stages down to something that we can actually implement on a month-by-month basis. The adequacy of the existing tools is quite different depending which of these two objectives we seek. So what's the existing technology that we have? All the methods that we currently have in terms of open pits are based on the concept of a sequence of nested pits in which the pit limit is determined based on increasing mineral value. So we say, what is the pit going to look like at a price of $1? What will the pit look like at the price of $1.10, $1.20, $1.30, and so on? And we don't have very many constraints on what those stages will look like. Mainly we just have constraints on the pit slopes and the pit bench widths. Then the scheduling, which determines our cash value, is based purely on benches within a stage. So we design where our stage is going to be, we select a sequence of stages of mining, then we schedule the benches within each one of those stages. Definitions relating to cutoffs of the equipment are already predetermined in terms of the selection of what will be ore, what will be waste, what will be going to the heap leach or to a stockpile or a dump. So the commercial life of mine planning tools that we currently have aid in the selection of mining stages and generate an optimal or a maximal NPV based on the definitions of these benches within a stage. And this is just an example of how these are generally generated. So if we had 8 different price factors, for instance, in a very, very simple deposit geometry, then we would generate 8 shells of equal increase in size. Now, it's not typically this way. This is just a simple example to explain what we're talking about in terms of the generation of price shells. And another example taken from the case study that we'll be looking at, another case study, not the one we're looking at today, is given here. So initial shell showing the access ramps. This will be the shell after some design has been taking place in terms of what the final shell will look like. The next successive shell, a fourth shell, and a final pillar. It's important to understand that these shells are not actually ever realized at any given point in time necessarily. They just represent designs towards which we're working over the evolution of the life of the operation. So there are some weaknesses in the current technology. The bench geometry that we're generating is a consequence of the pit shell. And the pit shell geometry is largely just a function of economics. It's a function of the value of the blocks in the block models and the price factors which we apply. The production of the materials coming from these benches is being produced without any consideration of the location within the bench. So the schedule is saying that you will produce so many tons of ore, so many tons of waste from a bench in a year. And you have no idea where that material is actually coming from within the limits of the bench. There are additionally no considerations of operational constraints, such as how we're going to haul and route material from those benches to the dumps. We don't take into account dump construction. We certainly don't take into account in-pit dumps. We don't take into account the accesses to each one of the pits. And finally, all of these packages are focused on maximizing the net present value of the project. And net present value driven solutions are not necessarily going to be feasible within terms of operational constraints. They do not take into account considerations having to do with maximizing utilization of capacity of different unit operations, for instance. Now here's an example of an alternative approach to illustrate what I'm talking about in terms of one of the weaknesses of the existing technology for life and mine planning. Here we have a blast master, which is basically a division of the benches within the pit into drill blast units. So we're scheduling not individual benches, we're actually scheduling the drill blast units within the pit. And I'm showing in the upper right-hand corner an entire pit with drill blast units. And then we're selecting a single bench in the bottom right-hand corner, showing a schedule probably associated with monthly productions or quarterly productions from that particular blast master on that particular bench. So you have much more detail here in terms of how you're actually going to operate, how you're going to produce from this particular mine, how you're going to schedule that, how do you go from annualized schedules on the bench to more detailed, operationally feasible schedules on that bench. So in summary, what's the problem? Black box solutions, existing commercial software, they predefine the input. They predefine the input as being benches within stages. And they also predefine the output, which is going to be an NP maximizing schedule based on production coming from somewhere within those benches in those stages. They also predefine what the objective function is going to be, which is NP maximization, and the constraints, which are very limited. So what we're doing with an NPV-driven schedule is we have to ignore operational requirements and constraints. So in summary, operational optimization tools that are designed for economic evaluation of new projects, which work quite well, are being applied to brownfield studies, such as existing operations. And for complex operations, these tools simply do not work. The solutions being generated simply do not produce operationally feasible solutions. So, under what circumstances will these existing life of mine planning tools work? Well, they'll work when they're applied to single pits, because these tools all function on the basis of single pit optimization. And when those pits produce similar ores. So we can have multiple pits, but they have to produce very similar ore types, so we don't have to worry about blending problems. Also, the geometries associated with those stages have to be relatively simple, and the mining sequences for the benches within the stages also have to be quite basic and straightforward. There can't be any serious or complicated constraints associated with blending of different types of materials or different grades or different contaminants. There can't be any issues relating to mill throughput rates as a function of ore hardnesses, or any restrictions on metallurgy in terms of recovery. So we can't have any severe concentrate penalties as well, because that would be, again, a blending problem. Your operational implementation would not be a concern. Again, you're just trying to establish the value of the pit, or you have an operation which is quite straightforward, and we're not too worried about operational requirements. But when will these not function? When will these existing tools not function well? Well, they won't function with underground mining. So if you have an underground operation, you have to go through considerable manipulation of the data to put it in a format that would be similar to the format of benches within pits. And you also cannot mix underground and surface operations using these tools. Like, again, if we have complex geometries or complex sequencing constraints, these tools will not work. And also, if there is any need for global optimization, where we have to look at multiple unit operations being optimized simultaneously as part of a life of mine plan, these tools will not work. They cannot handle serious blending constraints. They cannot consider penalties in the concentrate. And then finally, if there are complex or difficult operational requirements, such as very high stripping ratios at a given period during the life of the operation, then these cannot be resolved by the tools that produce annualized schedules based on entire benches. So I'd like to present an example of an alternative approach. First of all, we're going to dispense with fixed input-output black box solutions for these more demanding problems. And we'll use a level of planning detail which is appropriate for the problem being solved. So if we want to schedule benches within stages, we'll do that only when it's appropriate, only when the level of study requires a high level of detail. We'll also apply a top-down divide and conquer solution strategy, meaning that for annualized schedules or life of mine plans, yes, we could use benches within a stage, but we need to have a procedure that allows us to subdivide those benches into finer scheduling units so that we can also schedule on a medium-term quarterly schedules out to, say, 3 years. The way this can be done, and there's other ways, but this is a very useful way, is to use linear programming, mixed unit programming technologies to formulate the model which is appropriate to the problem being solved, which are appropriate to the projects. To use an objective function which is appropriate for that company, and to apply the appropriate decision variables and constraints for that operation, such that we can produce operationally feasible life